Good morning and welcome to Tech 293. This is where we left off last time. We had defined a bunch of terms and talked about how we would measure them. And we left by talking about these four different stress strain curves and how we could identify whether each material specimen was ductile or tough or rigid or strong or brittle just by looking at this stress strain curve. So I'm not going to review all of that right now. You have it in the video from last time. So if you have any questions about what any of those terms mean, make sure and go back and watch that video again. And then if you still have questions, then let me know, and I'll be happy to answer any questions about those terms that we talked about last time. But for today, let's keep going. There are a few more things that relate to tensile testing that I want to talk about today. The first is the idea of true stress versus engineering stress. And so remember that our definition of stress in general is force divided by area, right? It's the force that's being applied divided by the cross-sectional area of the part. Like if you cut it in half, what's the cross-sectional area? The problem is, if you think about this for just a little bit, you'll realize that as I pull this apart, this cross-sectional area, it changes. It changes during the test, right? And we know that. We have necking, but even before necking, we have a reduction in the cross-sectional area somewhat. So there's basically two different ways to think about this. The simpler way that we are going to do it in this class, and that is more commonly used, is called engineering stress. And the engineering stress is this one right here. It's the force applied at that point in the test divided by the original cross-sectional area. So A sub 0 or A sub naught, that means the original cross-sectional area. So basically what engineering stress is, all right, I know that the cross-sectional area is going to change for the part as I'm doing the test, but you know what, I don't care. And that's the simplest way of dealing with it, and that's also the most common way of dealing with it. So that's what we're going to do in this class. So you should be relieved to hear that. However, there is another way of doing it. I want you to at least know what it is, and it's called true stress. So the true stress is equal to the force applied at that time divided by the cross-sectional area at that time. All right, so the cross-sectional area is constantly changing. I mean, it doesn't change a whole lot in the elastic region, not a whole lot, but once you get into the plastic deformation region, it starts changing quite a lot. And especially once you get to necking, then it's changing a real lot. So if you really wanted to calculate true stress, then what you'd have to do is stop the test frequently and measure the diameter and then calculate the cross-sectional area in order to get the true stress. So I want you to know that true stress uses the true or real time-varying cross-sectional area as we're going through this test. Engineering stress does not. Engineering stress just uses the original cross-sectional area of the part. So, which is bigger? Which is bigger, true stress or engineering stress? All right, so let's say if we plotted true stress and engineering stress, which would be larger in magnitude? All right, well, think about this equation. All right, the area is going to be decreasing, right? The area of the specimen is going to be decreasing. So if our denominator decreases, we're dividing by a smaller number, what's going to happen to the result? Stress. Well, if you divide by a smaller number, then your result is going to be larger, right? So what we could say, and this is true, true stress is going to be larger than engineering stress. They're going to be real similar in the elastic region before there's much difference. You know, the cross-sectional area just doesn't change very much until you get to the plastic deformation region. But it's always going to be true that the true stress is going to be equal to or larger than the engineering stress, because this cross-sectional area is going to decrease during the test. So if we actually divided by that decreasing area, then our resulting stress would increase throughout the test, and it would be larger than the engineering stress. Okay, and that's basically what this says down here in different words. So here's what it looks like. If we were to plot that stress-strain curve, stress versus strain, they're real similar in the elastic region, but the yield stress looks like maybe somewhere around right here. And our true stress continues to increase like this. And our engineering stress comes up to a peak. We call that the ultimate tensile strength, and then it decreases. By the way, I'll say something real quick as a kind of an aside. It's kind of confusing to people sometimes to think that the stress actually decreases after the ultimate tensile strength. Some people like that's weird. That's weird to think about. But if I give you an example, I bet it's not that weird to think about. Think about silly putty, all right? I think most of us have had some experience with silly putty. Or it could be, I guess it could maybe be Play-Doh. It doesn't work quite as well, but anything kind of malleable and ductile. All right, so take your silly putty, or just imagine taking it, and you're gonna pull it apart. And initially, it's pretty difficult to pull that silly putty apart, right? But you stretch it, and then eventually, as you stretch it way out, so there's just a little string in between these two hunks, the amount of force required to continue stretching it apart, it decreases a lot, doesn't it? So once you've just got this little thin string between these two sections of silly putty, then the amount of force that's trying to hold them together is actually really low. So that's what we would be seeing in this section right here, as we are decreasing down from the ultimate tensile strength down to the point where eventually it fails. So this is not really that conceptually difficult to understand if you just think about something like silly putty or Play-Doh or something and pulling it apart. And yeah, the force required and thus the stress required to pull it apart after a certain point right here, it really does decrease. The force actually does decrease. And you will see that in the next couple of labs as well. Here's another plot. The blue here is the true stress, and the red is the engineering stress. So once again, I just really wanted to point out how the true stress is always going to be either equal to or greater than the engineering stress. And we've talked about all these different regions, so this should all make sense. You should be able to label these. You know, this would be a good test question. If I asked you to label, this actually be a very good test question. I might do this. I give you a stress strain curve, and I give you a bunch of points, you know, point A, point B, point C, region D, region E, and you have to label the yield stress, the ultimate tensile strength, the failure strength, the elastic region, the uniform plastic deformation region, the necking plastic deformation region, all of those things like that. All right, so make sure you're familiar with the important points on stress strain curves, and you'll get practice with that in the next couple of labs as well. All right, here's a little bit of a food for thought. Let's say you're designing a part. All right, so you're designing a beam for a chassis for a car body or something like that. It doesn't matter, whatever it is. A beam for a bridge, something like that. So which is more important for you to know to work with? Is it more important for you to know the yield strength or the yield stress of the material, or is it more important to you to know the ultimate tensile strength, aka ultimate tensile stress of the material? What do you think? What do you think? Which is more important? Now, oftentimes I get varied responses when I ask this in class, but oftentimes I get people say the ultimate tensile strength is more important because that's the maximum strength of the material, right? So it's not going to fail until it reaches the ultimate tensile strength. But remember that with the ultimate tensile strength, we get plastic deformation first before we get to the ultimate tensile strength. Do you want plastic deformation to occur in the support beam in your vehicle chassis or in your bridge beam? You know, when a really heavy semi-truck drives over your bridge, do you want plastic deformation to occur in your bridge? And usually when I phrase it like that, usually people are like, oh, yeah, not really. I don't really want my bridge to permanently change shape when a semi-truck drives over it or something heavy like that. So most people then kind of realize, oh, yeah, I guess the yield stress is probably more important to a designer. And that's true. That's true. Because with the yield stress, yeah, you get some temporary deformation. And, you know, it's true that when a semi-truck drives over the bridge is going to very minutely change shape, right? Just like this reminds me of watching a train pass. You ever watch the train go by and watch the rails or the ground underneath the train? It gives every time the train wheels go over the ground. So there actually is deformation in the rail and the ground underneath it every time the train wheels pass over it. But anyway, what I'm getting at is that temporary deformation is okay. There's nothing really wrong with it. You know, another example is the snow on the roof. As the snow is on the roof overhead, there's a good chance that the roof is going to deflect, hopefully very slightly, not very much, but a little bit. But if I designed the roof such that it would be close to its ultimate tensile strength when the snow is on it, then the roof shape would not come back to what it was originally, and that's a problem. So as you're designing things, temporary deformation, probably okay, probably fine. Plastic deformation, usually not okay. So therefore, the yield strength or yield stress of the material, I would argue, is more important than the ultimate tensile strength or ultimate tensile stress of the material. And this is going along with what I just said. So when you're designing something, avoid exceeding the yield stress. Usually you have safety factors. So not only do you not want to exceed the yield stress, but usually you're going to have a safety factor of 2 or 3 or something like that. So really, you don't usually want to get to even half of the yield stress or 1/3 of the yield stress. That leaves room for unforeseen circumstances. You know, you get a once-in-a-century snowfall or once-in-a-century windstorm, things like that. So you leave a little bit of overhead room for unexpected things, like all of those examples where you're not necessarily expecting that to happen, but design it so that your part doesn't break if you do get those occasional really heavy loads. So a recap here from this is really just finishing up the presentation from last time. We're going to use a UTM, Universal Testing Machine. The stretch of the material is going to be the independent variable. The force is going to be the dependent variable, so it'll be on the vertical axis. We need intrinsic properties, so therefore we convert the force to stress by dividing by the cross-sectional area. And we convert the stretch to the strain by dividing by the original gauge length, which is this length right here, of the specimen. The elastic modulus, or the modulus of elasticity, is equal to the change in stress divided by the change in strain. In other words, it's the slope of the elastic region of the stress-strain curve. To calculate it, pick 2 points on the linear elastic region. Take the rise over run, so the change in the stress divided by the change in the strain in the elastic region. The yield strength is the stress at the end of the elastic region once you start to get, or you're about to start getting plastic deformation. Ultimate tensile strength is the peak of the stress-strain curve. You should know that ductile materials versus brittle materials have to do with the amount of plastic deformation that you'll get, and toughness is the area under the stress-strain curve. All right, so what I want to talk about here is actually this region of the stress strain curve right here, because we haven't talked so much about this region. We said there's necking going on over in this region. We said there's elastic deformation going on in this region. And so far we've said that there's uniform plastic deformation happening in this region between the yield strength and the ultimate tensile strength. But what's really going on at a molecular level in that region? And what it is, it's called work hardening. That is the work hardening region. And if we think about this from a lattice perspective, what's happening is that as we start to get plastic deformation, we start to get defects in the lattice structure actually migrating and moving through the lattice structure. As you're pulling the lattice structure apart, you know, in elastic deformation, you're just stretching the lattice and then you let it go and it returns. It's like stretching it and returning it. In plastic deformation, you get some defects like right here in the lattice structure. Lattice structures are not always perfectly three-dimensional in all of the different dimensions. They're not perfect crystalline structures. It's very rare to have perfect crystalline structures. So there's oftentimes defects in these, like right there. And then as we pull on it, what's going to happen is that's going to move. And now the defect moves over to here. And then I keep pulling on it, and the defect moves over to here. So I'm going to cause these, they're called dislocations. The defect is dislocated. I'm causing dislocations in the material, which means the movement of the defects within the lattice structure. All right, but then think about if there's a grain boundary over here. There's a grain boundary, and the lattice structure over on this side over here is at a totally different angle, a different orientation. So it's going to be difficult to impossible for that dislocation, you know, that defect to continue migrating into the next grain. In most cases, it can't. You can't continue to have the defect migrate from one grain to the next grain to the next grain. And I kind of alluded to this before when we talked about grains a couple of weeks ago. And this is why grain boundaries are so important and have a big impact on the mechanical properties of the material, because defects in the lattice structure can move within an individual grain if you pull on it and cause plastic deformation, but they can't usually move into the adjacent grain. And so the grain boundary and the density of the grain boundaries, which is impacted by how large the grains are, those have a really important role to play in the mechanical properties of the material. All right, so what happens is in between the yield stress and the ultimate tensile strength, you're starting to get plastic deformation to occur. So you're starting to move these defects. And generally what happens is the easiest ones to move first. So as I pull on this beyond the yield stress, I get plastic deformation, and the easiest defects to move to cause dislocations, those happen first. And then as I continue pulling on this specimen, I get more and more of those defects to move until you can't anymore. You don't have any more defects to move. And at that point, you're basically at the ultimate tensile strength. So the reason that the ultimate tensile strength is higher than the yield strength is because as I pull on this material and I get more deformations to move, each successive deformation, each successive dislocation of a defect becomes more and more difficult than the previous one. All right, so that's why the stress continues to increase between the yield stress and the ultimate tensile strength. And that's why the ultimate tensile strength is greater than the yield stress. All right, so the next couple of slides are really just kind of a preview to solving tensile test problems. All right, so first of all, this is very important. If we are doing a calculation problem and we find out that the stress is greater than the yield stress, right? So here's the yield stress right here. If we're doing a problem and we calculate the stress and we find out that the stress is greater than the yield stress, well, that's fine. You know, maybe the question is just what's the stress? So, okay, that's fine. But if you are doing a problem where you want to calculate the change in length, or you want to do a problem that uses the elastic modulus, you can't. The only time you can use the elastic modulus is if you're below the yield stress, all right? So that's really important to know. The only region where the elastic modulus is valid, is defined, where you can use it, is below the yield stress in this region right here, okay? I need to stress that so that you don't try to use it for some stress value way up here. All right, so what I'm going to say here is that there's really only 3 equations that you need to know. This whole section of tensile testing, there's only 3 equations. And we know them all already. We have our first equation, which is for stress. Stress equals force divided by area, or load divided by area. Sometimes we call it load, sometimes we call it force. But stress is force divided by area. The next one is strain. Strain is the change in length, otherwise sometimes called the stretch, divided by the original length of the part. And the last one is for the elastic modulus, which is convenient because it gives us a relationship between the stress and strain. So the elastic modulus equation is kind of like an intermediary between the stress equation and the strain equation. And the equation for that is that the elastic modulus equals the change in stress divided by the change in strain. All right, so this is our third equation, the elastic modulus equation. That's it. With those 3 equations and some algebraic manipulation, just rearranging those equations, we can solve a whole bunch of tensile test problems. There's basically 2 types of problems that I can give you. One is we know the load, all right, or the force, all right? So I have this specimen and I apply a given load to it. I suspend 100 pounds force from this. What's the change in length? That's one type of problem. The second type of problem is I've got this specimen right here and my design allowances, say it's a bridge beam or a vehicle chassis member, and my design specifications say that it can change in length by up to whatever, you know, 1/10 of an inch or 1/4 of an inch, something like that. How much load can I apply so that it will change in length by that amount? All right, so that's the specified change in length. What's the load required? A couple things to remember. Remember that the strain refers to the change in length of the narrow section, the gauge length section right here, divided by the original length of that section. And second of all, like I just said, you can only solve these problems when you're in the elastic deformation region. You get into the plastic region, it all goes out the window. It's not linear. It's not linear anymore, and there's no simple relationship between stress and strain. The reason we can solve these in the elastic region is because there's a simple relationship between stress and strain. It's given by the elastic modulus. But that doesn't apply once we get into the plastic deformation region. All right, so here's the first type. This is a known load or known force. What is the change in length of the part? All right, so first of all, what you could do, you can go ahead and calculate the modulus of elasticity, E, because you're probably going to have to use it. In any of these problems, you're going to have to use the elastic modulus, so you may as well solve it. Remember, it's the slope of this line, the change in stress between 2 points divided by the change in strain between these 2 points, say right there and right there. All right, so you got the modulus. You can calculate that, and you will calculate that for the next couple of labs. Then when you do the calculations, first what you're going to do is calculate the stress, because you know what the load is, right? That's in the problem statement. The load, the force is known. It's given in the problem statement. This cross-sectional area is either known or you can compute it. The area of a circle is pi r squared, so you can compute the cross-sectional area. Now you know the stress in the part, and you can use the elastic modulus value to calculate the strain. So now just rearrange the equation for the elastic modulus, that's this one right here, rearrange this equation and solve for the strain. And you'll find that the strain is equal to the stress divided by the elastic modulus. The stress you just calculated here, the elastic modulus you calculated at the beginning of the problem from the experimental data. So you know both of these now, so now you can find the strain. And lastly, rearrange the equation for strain. Remember, strain is equal to change in length divided by original length. Rearrange that equation to solve for the change in length, and you'll find that the change in length equals the strain times the original length, which is the gauge length, which we know. So this we just solved for up here. This we know, or we can measure, so we can find what the change in length is, and that's our problem. So this is kind of like a 3 or 4 step problem. So I'd say 4 step, because first you calculate the modulus, and then you do these 3 calculations with the definitions of the equations that we have. All right, so that's how to do that type of problem. That's approximately half of all the problems that I could give you in this section. The other approximately half is, all right, you have a specified length change. We're allowing this to change by a certain length. How much force can it withstand so that it changes by that amount? All right. So once again, you're probably going to need the elastic modulus. So you might want to just calculate that right away off the bat using the definition of the modulus, change in stress divided by change in strain, rise over run of the linear elastic region. And then the steps that you'll follow are, all right, we know what the change in length is. That was given in the problem statement. We know what the gauge length was. That's this length right here. Now, what is the strain? We can calculate that. So we can calculate what the strain in this part is going to be. And then we can use our definition of the elastic modulus. We can rearrange the equation a little bit, and we can find what the stress is. So you solve for the stress in this equation up here, and you find that the stress is equal to the strain, which we just calculated, times the elastic modulus, which we calculated initially in the problem. So with that, you can calculate what the stress is. And then lastly, if you know what the stress is and you know what the cross-sectional area is, which you can calculate, if you know the dimension of the part, then you can calculate what the load or the force is. All right, so rearrange the stress equation and you find that the load or the force equals the stress times the cross-sectional area. And you know that because you just calculated it. And you know this because you know the dimensions of the part, or you can measure it. So with that, we can find our load force. So that's how much load force you can apply so that the part will change in length by a specified amount. All right. I probably should be indicating that here to indicate the gauge length change by a certain amount. All right. Okay, that's going to wrap things up for this video.